Hello and welcome back to Let's Code Physics. I am very excited to share this video with you today because today marks the 1-year anniversary of our very first Let's Code video on this channel. Let's Code Physics is 1 year old today. I'm very excited to get to celebrate that with you today. That first video, you may recall, was this police car chasing a speeder. I'll include a link to that series in the description below. It turns out that police officer is still chasing the speeder. I decided to pull that code out again and take another look at it, play around with it a little bit more. You may recall the problem we are facing is that we have a speeder whose position is represented by this array XS for X position of the speeder. He is traveling at a constant velocity that is greater than the speed limit, which is why the police officer, whose position is represented by XP, or X position of the police officer, needs to accelerate from rest and start chasing after him. And there may be more to the story. You know, the speeder may be off to rescue somebody, or maybe they just robbed a bank. You know, you can fill out the story in your head. But either way, the police officer is giving chase, and in order to do that, the police officer needs to be accelerating. And in order to capture that acceleration, we implemented the good old Euler-Kromer method, where we first increment the police officer's velocity by his acceleration times the time step. Then we update his position by using his new velocity, again multiplying by the time step. And we also implemented a maximum speed for the police officer, so his position versus time graph will ramp up and will then level out at a nice steady slope eventually. Ideally that maximum... excuse me. No, that's something I added in later. Excuse me. Never mind. Forget that right now. Ignore the man behind the curtain. We'll get to that in a second. And what we got were these results that looked basically like this. The blue is the speeder's position versus time. So that is a nice diagonal line because it's constant velocity. Constant velocity gives you constant slope on position versus time graph. The police officer is accelerating, so his slope is increasing as he goes forward. We did not set a maximum speed. That is my bad. I never said that. In fact, I think I can go and edit that. No, I don't think I will. I put too many cuts in my last video. I don't want to edit anything now. And the graph terminates, or the program stops where the police officer, the green curve, catches up with the speeder, the blue curve right here. So basically where the two intersect. And then the program spits out the distance that required. So the distance is about 864 and some change meters. So he's catching him here at this point, and it takes 24 seconds, which is the rightmost value on the time axis. And so that was a neat problem. We did a lot of neat things with it. One question that arose during discussion about that video is, what about traffic? What happens when cars get in the way of the police officer? Well, to model actual traffic on the road and the police officer swerving around, that would be a really neat thing to model, and I will probably do that probably in the spring. I'm not going to do that in Scilab, though. I will probably do that in either VPython or my new favorite, Unity, where I'm programming black hole battles. So if you came back for the police chase, please do go check out Black Hole Battles as well. Really exciting series. I'm really happy with it. But the way I would like to model that is through a series of probabilities. So let me take you up here to the stuff that I've added to this code this past week. Everything is modeled the same. We're not including the reaction time because we saw that didn't make a huge difference. Here's the police officer's acceleration at approximately 3/10 of a g, basically. But what we're doing now is we're adding in this probability of the police officer encountering an obstacle. And since I've been programming in Unity, I'm on the camel casing kick there. So so all my new variables are camel cased. But this is the probability that gets evaluated every second that the police officer encounters a traffic obstacle. Now, we've got two kinds of obstacles that the police officer can encounter. One is that the police officer has something that he needs to swerve around. So this, for example, would be a slower moving car ahead that the police officer sees and that he's able to approach swerve around, and then get back in front of. And so that's going to produce a slight reduction in velocity, but it's not going to take his velocity all the way down to 0. It's going to effectively decelerate him as he goes around. So even though his speed, the magnitude of his velocity vector might be constant as he turns, the forward component of his velocity is going to decrease, and then the forward component of his velocity will increase. The other possibility, so that's a swerving, that's down here. The other possibility is something that causes him to have to slam on brakes. So this is where a car has stopped in front of him, or a tree falls over, or something else happens right in front of the car, and the police officer has to slam on brakes, immediately come to a stop. Actually, does he come to a stop? I think he comes to a stop in the code. And so what I've done is I've given those two possible outcomes two different acceleration values. I'm calling them decel. I know I don't usually like the word deceleration, but that just helps keep it straight. And I've gone ahead and made those negative. I actually made the mistake of making those positive earlier, and it screwed up my code. So there we go. Well, I didn't make them positive. I made these values negative, and then I put minus them later on. So negative gives a positive. Anyway, so when the police officer is slamming on his brakes, I looked up this value that for professional drivers on a closed course, 2/3 of a G is kind of the fastest that they slam on their brakes. So this is kind of an upper level value, being 6/10 of a G. So it's a little bit shy of 2/3. So it's 6 instead of 6.67, basically. Just so that our, because let's to better model a police officer in the real world. And then this is the deceleration for swerving around. So this is just 1/10 of a G. Again, this is just he loses a little bit of velocity in the forward direction. And then we also need to keep track of whether the police officer is in the middle of swerving or slamming his brakes. These are logical variables that just keep track of that. They get initialized to false. But let's talk about this probability for a second. So there's really three probabilities we're interested in. The first is the probability of there being an obstacle, period. Now, currently I have that set to 0. So there is a 0% chance that the police officer encounters an obstacle, and that's why we get the same results that we got a year ago, the 864 and the 24 seconds. Nice, steady acceleration for the police officer. That gets evaluated down here. So the speeder is unimpeded, so we'll pretend that the speeder doesn't encounter those obstacles, although I suppose it would be fun to add in the same probability for the speeder. Then the police officer has a better chance of catching him, I guess. Or I suppose, no, the way I need to model that when I do this full-fledged, like with an animation, is to have like a 2-dimensional grid for the streets and have the speeder start taking turns and things like that. Oh, that'll be fun. Okay, we'll do that in the spring, I think. Or maybe I'll save that for the 2-year anniversary special. I don't know. So this first evaluation is whether there is an obstacle, period. Okay, so the first thing it does is there an obstacle? And so it's only going to evaluate that if he's currently not swerving or slamming. So if he's in the middle of swerving, we're not going to have him encounter another car that he has to swerve around again. Same thing if he's slamming on his brakes, he's not going to then encounter another thing and have to slam on his brakes again. So if there's not a swerving or slamming in progress, then we check for whether this random value that we assign here to the variable obstacle is less than the probability of obstacle. So if prob of obstacle is 0, then this cannot possibly be less than prob of obstacle, because this random variable that gets assigned here is between 0 and 1. Now there's also this extra if here, this if modulo time. I added that in after I first added in the rest of the stuff, because this keeps you from punishing the police officer for a smaller time step, because if you take out this part, then it evaluates this probability every single time step. So if you decrease the time step, then the police officer is more likely to encounter an obstacle per second, which isn't really physical. I mean, whether the universe runs on seconds or milliseconds, that's not really going to change whether there's something in front of the police officer. So this is just to enforce that the probability is checked once every second of simulation time. So our time step is 0.01, so that's why I made the modulo less than 0.01. So this is when it gets to second 1.00, it checks. When it gets to second 1.01, it does not. When it gets to second 2.00, it checks. When it gets to second 2.01, it does not, etc. So that's helpful because that way we don't end up having, lots and lots of probabilities, which we were. The other way to do that would be to rescale this probability based on dt. Although that's going to make that number smaller, and so then there's a smaller chance of your random number generator selecting it. So I think this is probably the best way to go. If you want to post a different way to have it scale the probability for the time step, let me know. I'd love to see that feedback in the comments. So let's say that it does select an obstacle for to be in the police officer's way. So let's say it does meet this condition that this random number is less than probability of obstacle. So if we made prob of obstacle 0.3, this would have to be between 0 and 0.3, which that's a 30% chance of being selected between 0 and 1. So there you go. There's your probability. So here it again randomizes because now we have to determine which type of obstacle it is. And so here's where we've got the probability of slamming on brakes and the probability of swerving, which I guess I don't actually need the probability of swerving because I just have an else there, because if there is an obstacle, it's going to be one or the other. Either way, what you set up here is the probability of slamming on the brakes. So currently that is 0.01 or a 1% probability. Now that's a 1% probability given that there's already an obstacle, right? So this is a conditional probability. It's not he has a 1% probability of slamming on his brakes every second. It's if there is an obstacle, there's a 1% chance of him having to slam on his brakes. I'll put a link to a description about conditional probabilities in the description below. Wonderful stuff that gets kind of counterintuitive in your head, conditional probabilities. And so the probability of swerving, which we don't actually use, I just realized is going to be 1 minus probability of slamming, because if there's an obstacle, it's going to be a slam or a swerve, basically. So what do we get here? So if basically if we have the same setup here where if the new random variable is less than probability of slam, then we're going to say that slamming equals true, and we'll take care of all the math regarding that down later on. The reason we want to do that is because slamming is going to last more than one iteration of the loop. So it's going to keep track of whether we're in the process of slamming on the brakes or not. And the same thing here. Otherwise, if he's swerving, then we set swerving equal to true. We also keep track of what speed he's going to get to during the swerve. So remember, when he's swerving, he's going around, so he's losing some of the speed, but he's not stopping. Slamming is he's coming to a stop and having to start over again. So we come down here, and this is where we take care of calculating the acceleration. Let's start actually at the bottom and work our way up. So if we're not slamming and we're not swerving, then his acceleration is the normal 3.0 that we defined up above right here. Otherwise, let's go up here. If he is slamming on the brakes, then we check to see whether he's done slamming on the brakes, right? So this is he's in the process of slamming on the brakes. So slamming on the brakes takes his velocity down to 0. And so once he reaches 0, then he's ready to resume accelerating. And so we set AP back to its default value, and we set slamming to false because he's no longer slamming on brakes. He's now moving forward. Otherwise, his acceleration, the one that we use down here in the Euler-Kromer method, is his slamming deceleration, that hard negative 6.0 meters per second squared. That's at 6/10 of a g that I'm sorry to be putting this guy through. And then if he's swerving, then we do the same type of check here, where once he reaches the swerve speed, he exits the swerving maneuver. We reset the acceleration value, and otherwise we set the acceleration value to the swerve deceleration there. And then, of course, that AP value, so there's 3 possible AP values. He can be at his regular positive 3.0, he can be at negative 6, he can be at negative 1, and that value gets fed down in here, and then that just impacts everything else down here. Now, I'd like to know when he's slamming on the brakes and when he's swerving, so I put in little print statements to tell me when both whether he's slamming or swerving and what time that's happening at, so that we can correlate that with a graph. So like I said earlier, right now there's no slamming or swerving going on because the probability of encountering an obstacle is 0.0. So let's increase that. Let's say that every second there is a 10% chance that he is encountering an obstacle. So that's 1 out of every 10 seconds. So we would expect in the run of 24 seconds that there would be, around 2 obstacles. Let's see if we get that. Okay, he did have to swerve. He had to swerve at 20 seconds. So let's take a look what happens at 20 seconds. So before that, everything is accelerating as usual. He is going on along his nice acceleration route. But then at 20 seconds, he encounters a swerving, so he has to reduce his speed to 95% of his previous speed. Not a huge deal. It changes the time that it requires from 24 seconds to 25 seconds. So that one minor encounter increases the catching time by 1 second. That could be significant, right? I mean, 1 second could be the difference between the speeder getting over a drawbridge and the policeman getting stuck. Actually, what I'd like to do, let's keep that graph on there. I recently installed the plotlib package, which lets me use the hold command so that I can keep the graph there from a previous run. Let's turn probability of obstacle back to 0. And 5. And now I get the previous graph. So this inner one is his previous one. So not a huge difference, right? So, okay, not a huge deal. But let's see what happens. Let's turn the hold back on. Let's see what happens when we... actually, the first thing let's do, let's change that swerve speed to... Let's make that 80%. Let's take that down a little bit. Okay, he did not have to swerve. Oh, I forgot to reset the probability of an obstacle. Let's put that back to 10%. Okay, we get a few swervings this time. Now, what's interesting is that this is going to compound, right? Because now that I've decreased that speed, it takes him a little bit longer to catch up with the speeder. And so the more time he has to use, now 59 seconds instead of 24 seconds or even 25 seconds. Now that's more than doubled. And there's more probability for him to encounter an obstacle. In this case, he encountered one at 5 seconds. So we see a little bit of change in the concavity there at 5. He encountered one at 11. There's another change in the concavity. We encountered one at 23. Yep, there's a little change in the concavity there. And he encountered one at 36. And after that, after he got over that, and you notice he encounters the swerving here, so it's concave down for here. He doesn't recover till about here, and then he's able to accelerate the rest of the way. So this is pretty delayed. I mean, this is more than double the amount of time that would require. What if we decrease this down to half? What if he has to swerve around so much that it's reducing his forward going velocity by half? Let's see. Oh, we're all the way to 90 seconds now. We're up to 120 seconds. Of course, if I make this too low, if I make it too bad, he'll never catch the speeder, and this code will never end. And then our anniversary celebration will never end. Okay, wow. Oh, look at this one. This one's interesting. So at about just before 120 seconds, or I guess, excuse me, that must be the 121. Yeah, so around 120 seconds at this swerving, he has almost caught up to the speeder, and then he has to slow down. And because he's going faster at that point, he has to slow down more, and it takes longer for him to get down to the speed that he needs to get down to, and then get around, and then get back up to speed. Wow, that's crazy. And now we're at 190, excuse me, that's not the... Yeah. We're now at 192 seconds instead of 24 like we had before. Oh, man. Let's put this up to 90. 95 was probably a little too high. So let's increase the probability of an obstacle. Let's see what happens if there is a 30% chance every second. So 3 out of every 10 seconds he encounters an obstacle. Okay, so we're now taking a minute. Just over a minute. We're taking 70 seconds. Yeah, we're taking 70 seconds instead of our previous 24. So now it's 25. It's almost tripled. It is almost tripled his ability to catch the time required to catch up to the speeder. Let's put this down to a more meager 20 seconds. Or not 20 seconds, 20%. Okay, so this one is not quite as bad. Of course, it's all in the random distribution, right? So this is all a matter of when the random variables how the random variables get picked. So like that one still took 77 seconds. If we run it again, it can take a different amount of time, right? That one only took 36. So I suppose another thing to measure would be the standard deviation of the time in addition to like taking the average. Here's what I want to play around with though, is I want to change the probability of him having to slam on his brakes, because that is going to be a big deal. Okay, so we've been getting things anywhere between 30 and 70 for our current setup. Actually, has he had to slam on brakes any in the simulations we've been looking at? Swerving, 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 swerving. No, okay, he has not had to slam on brakes any. So let's increase this to a more appreciable value, more noticeable value. There's nothing appreciable about getting in the way of a police officer. Did he have to slam on his brakes any there? Okay, he didn't have to slam on his brakes any there. We're still getting a time within the range that we've experienced. Okay. You have to slam on his brakes any here. Oh, that looks like he did have to slam on his brakes one time. Okay, so he had to slam on his brakes once at... Oh, that's right. This thing will spit out the time first and then the... No, it'll print out slamming and then the time. Okay, yeah. So now he had to slam on his brakes at 20, because I learned the display function is last in, first out, or first in, last out. So you put the first thing you want last and the last thing you want first. It doesn't make sense to me. So he had to slam on his brakes at 20. You notice his velocity. So he slams on brakes, his velocity becomes 0. So this graph becomes flat. So he is having to come to a stop here. So somebody has stopped in front of the police officer. Police officer has slammed on brakes. He's been going along nicely. Then he slams on his brakes. And then he continues. Then he has to continue forward. He basically has to start over. And you look at the distance that the speeder gains on him during that time. I mean, that's just nuts. Let's try one more with that probability. Oh, I didn't check the total time on that one. Total time on that one was 98 seconds. So a bit longer than we've seen previously. Here he only had to swerve twice, so that was nice. That was fortunate. Here he's having to swerve a bit more. Okay, he had to slam at... he had to slam a couple times. He had to slam 2 times in a row. And now it's taking a bit longer. It's taking 160 plus seconds. So, 180 is going to be 3 minutes. We were at 24 seconds, and now we're at almost 4 minutes for him to catch the speeder. And again, this is just with a 20% chance of there being an obstacle and a 10% chance of having to slam on brakes, and that required a whopping 274 seconds. 274. I'm not gonna embarrass myself by doing the math in my head. That's 4.5 minutes that it took him to catch the speeder. Let's look at all the times he had to slam on brakes. He had to slam on brakes here. 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 So instead of 24 seconds, a quarter of a minute, it's now gone up to 4.5 minutes. That is nuts. That is just wow. Oh, I didn't mean to exit that. Why did I do that? Yes, restore last session. Okay. I thought I was exiting the graph. Wow, that is nuts. Let's see. What else could we change with this thing? Let's be even meaner. Let's say it's a 20% chance of slamming on the brakes. Now this is going to take a while to run, I'll bet. Oh no, it did not. Because it depends on whether he encounters an obstacle. Okay, so he had to slam on brakes early, which isn't such a bad deal because he hadn't gotten quite up to speed yet. He did have to swerve a few times, and you see what that does to the shape of the graph there. Let's do one more. Okay, he had to slam. He just had to slam one time, I think. Yeah, oh no, there's twice. There's once at 20 seconds, so there's once there. I thought I saw another one. He had to slam at 73. Oh, now that's interesting. Okay, so he had to slam on his brakes here. He had to slam on his brakes at 73, but he didn't slow down enough to get to 0 before he caught the speeder. So that's a little bit unphysical there. But you can see just having the one slamming and a few swervings, brought it to 78 seconds. Wow. So the moral of the story, kids, is when those police sirens are blaring on the road, get out of the way. It's in the math. We've mathematically proven it that you need to do that. Cool. Or not cool. I mean, it's in the math, so do it. Okay, well, that was fun. That was really neat to see. I love seeing graphs that are not your usual parabolas and things like that. And yet it's made out of parabolas, right? So you can model this as a parabola here, join it with a parabola here, join it with a parabola here. It's piece-wide, but it's still made of parabolas. It's the kind of stuff I love. Anyway, thank you so much for watching. I really enjoyed this past year. I'm glad I got to return to the police officer. Be looking for another follow-up on this. I think in the spring we'll try to do a full-fledged 2D chase around the city, and we'll see what that does. So thanks so much for watching. I'll see you next time. Bye-bye.